For many years, geologists regarded Mount Rainier, Mount St. Helens and Mount Adams as independent volcanic entities, each formidable in its own right, yet geologically disconnected. That understanding has been dramatically overturned by new satellite-based InSAR imagery, which has unveiled a startling subterranean truth. A vast network of magma pathways lies hidden beneath the Pacific Northwest, interlacing these towering volcanoes in ways previously unimagined. The implications of this discovery are so profound that the United States Geological Survey has issued an alert, signaling that the volcanic threat in the region may be far more complex and potentially more perilous than once believed. Rather than isolated peaks, these mountains appear to be part of an interconnected system, a dynamic underground architecture shaped by molten rock. At the heart of this revelation is a massive, partially molten formation beneath Mount St. Helens, Mount Adams, and Mount Rainier. If confirmed, this would represent one of the largest magma bodies ever identified, rivaling even the immense magma reservoir beneath Yellowstone. While this doesn't automatically classify the region as a brewing supervolcano, the scale and nature of the discovery provide a rare glimpse into the Earth's interior, exposing geodynamic processes that are both awe-inspiring and unsettling. This concept of subterranean volcanic communication isn't entirely new. Indigenous oral traditions once described the volcanoes of the Cascades as if they were living beings, conversing like old friends. Modern science, long skeptical of such metaphors, has only recently begun to consider that these legends may have contained echoes of geological truths. What was once dismissed as folklore now seems eerily prescient. Not all scientists are convinced. Some remain cautious, citing the absence of telltale signs that typically accompany vast magma reservoirs, such as increased seismicity, surface deformation, and thermal anomalies. Seismological studies have so far not detected the characteristic seismic wave patterns that would suggest a sprawling pool of semi-molten rock. According to experts like Seth Moran of the USGS Cascades Volcano Observatory, definitive proof of a continuous magma body remains elusive. The research, led by scientists from GNS Science in New Zealand, employed a technique known as magnetotellurics to detect variations in the electrical conductivity of rock formations up to 20 miles below the surface. Because molten rock and underground fluids conduct electricity more effectively than solid rock, this method can reveal hidden magma chambers with impressive resolution. During extensive fieldwork, researchers endured grueling conditions, carrying 40-pound instruments, burying them in difficult terrain, and digging through rocky soil for hours at a time. The physical toll was considerable. One team member even developed stress fractures from the repetitive strain of excavation. This ambitious study began in 2006, coinciding with Mount St. Helens' most recent eruptive phase, a dramatic event that unfolded over 3 years. As ash and steam burst from its crater and molten rock flowed steadily from its core, magnetic measurements captured new insights into the vertical magma conduit feeding the eruption. More intriguingly, those measurements hinted at something even deeper, a connection extending nearly 10 miles beneath the surface to an electrically conductive zone that may link St. Helens with its neighbouring giants. Extending their investigations eastward toward Mount Adams, scientists discovered that this neighbouring volcano too appeared to be linked to a vast subterranean conductive zone. Their data revealed what seems to be a massive regional reservoir beneath the Cascades, possibly feeding at least 2 of the region's major volcanoes. Preliminary evidence suggests that Mount Rainier could also be connected to this system, though researchers emphasize that it's far too early to draw definitive conclusions. Rather than a fully molten chamber, this underground structure resembles a viscous, crystalline slurry. Only a small fraction, estimated between 2 to 12%, consists of molten rock. This contrasts with the long-standing view that each Cascade volcano is fueled by an isolated magma chamber, with magma rising from the Cascadia subduction zone where the Juan de Fuca plate dives beneath the North American plate. If, however, several volcanoes are instead sourcing magma from a shared reservoir, it would fundamentally reshape the understanding of volcanic behavior in the Pacific Northwest. Such a revelation inevitably raises a haunting question. Could this connectivity increase the risk of coordinated or mega eruptions? Experts remain cautious. The scenario of a super eruption like the one that occurred at Yellowstone 640,000 years ago is considered improbable for the Cascades. That eruption was driven by a unique geologic hotspot, a deep plume of molten rock welling up from the mantle, producing cataclysmic force. No such historical precedent exists for Rainier, St. Helens or Adams, which weakens any suggestion that the Cascades could produce similarly devastating events. Yet the discovery of a partially molten shared reservoir may explain how certain volcanoes manage to erupt thick, voluminous magma despite having comparatively small local magma chambers. The findings represent the most advanced imaging of this kind to date, offering tantalizing glimpses into the hidden dynamics beneath the surface. Still, the method based on conductivity measurements produces only a blurred outline, and many scientists suggest that what appears to be magma may instead be fluid-saturated sedimentary rock. The implications are as provocative as they are uncertain. In the words of one geologist, the hypothesis invites deeper exploration but demands rigorous scrutiny. Meanwhile, just 60 miles southeast of Seattle, the serene and majestic silhouette of Mount Rainier may conceal one of the nation's gravest geological threats. Unlike the violent eruptions of caldera volcanoes, Rainier poses a different kind of peril, one forged by its icy crown. If rising magma comes into contact with its thick glaciers, the result would not be a fiery explosion but a deluge. The ice would melt rapidly, generating lahars, deadly torrents of mud, rock and melted snow capable of obliterating entire communities downstream. In early 2025, subtle but troubling signals began to emerge. Minor earthquakes beneath Rainier's southern slopes grew more frequent and deeper. Satellites detected unusual heat near the summit, and sensors picked up alarming spikes in sulfur dioxide and carbon dioxide, gases often released as magma ascends toward the surface. Then, the most disquieting sign, the mountain began to bulge. Instruments recorded a slow, steady uplift, indicating that the Earth was swelling from within. As seismic instruments stretched from Washington to Northern California captured an uptick in geological restlessness, a strange new signal began to ripple through the data. It was not an earthquake, nor the roar of a volcanic blast. This phenomenon had no clear epicenter, no abrupt jolt or shockwave, only a low rhythmic vibration that returned like clockwork every 11 hours. It pulsed too slowly to be the product of traditional tectonic motion, yet its regularity was unnervingly precise. Scientists, both fascinated and unsettled, came to call it the echo. Mount Rainier, long revered for its beauty and feared for its potential, began to exhibit alarming changes. Glacial meltwaters turned opaque and sour, darkened by sulphurous compounds rising from below. Streams that had once flowed with crystalline clarity became turbulent, muddied torrents. The glaciers themselves were retreating at an accelerating pace, exposing raw earth and fractured ice. By late April, the United States Geological Survey issued a red alert, an unmistakable signal that the mountain's transformation had reached a critical threshold. As researchers attempted to isolate the origin of the signal, they were met with contradictions. Some data pointed to Mount Rainier as the source, while other readings suggested the signal might be radiating from the seafloor off the Oregon coast, near the volatile Gorda Ridge, a region riddled with tectonic fractures and rifts. One particularly unsettling theory proposes that the signal doesn't come from a single location at all, but is instead amplified through a vast subterranean structure. The rhythm, an unwavering 11-hour cycle, defied easy explanation. It was not an approximation, it was exact. More speculative theories began to surface, pushing the boundaries of geophysical understanding. A nearly identical subsonic signal was recorded shortly before the 2011 eruption of the Nabra volcano in Eritrea. At the time, the tremor was dismissed until the eruption shattered the silence and filled the skies with ash. After the emergence of a mysterious seismic signal near Mount Rainier, tremors began to ripple outward with unsettling speed. Within mere days, seismic instruments across Oregon and Northern California detected increasing activity. Mount Hood exhibited faint but persistent quakes, while Mount Shasta trembled under a new phase of unrest. Even Mount Lassen, dormant for generations, began registering unusual ground shifts. What initially appeared to be a localized disturbance had swiftly escalated into a regional phenomenon. Yet the most disquieting signals came from farther south. Along the southern stretch of the San Andreas Fault, seismic arrays detected harmonic tremors, low-frequency vibrations that often indicate underground fluid movement or mounting pressure within deep magma chambers. These signals bore a spectral signature that pointed not to randomness, but to a coordinated subterranean disturbance of immense scale. A once dismissed hypothesis has now captured the full attention of the geophysical community. The seismic disturbance beneath Mount Rainier may be setting off a chain reaction through interconnected fault networks, potentially threatening the stability of the entire Cascadia subduction zone. This idea, long confined to academic speculation, is now being debated with urgency in private meetings among top scientists. The evidence suggests more than a coincidence. The seismic swarms were not scattered randomly, they moved with uncanny precision, propagating in a deliberate north-to-south rhythm. To many observers, it resembled a deep, resonant signal coursing through the Earth's crust, an ominous overture that may foreshadow a much larger upheaval. The transformation from isolated volcanic tremors to a broader tectonic enigma has placed more than 50 million people along the west coast under a widening veil of uncertainty. Each tremor, each shift in the Earth, now carries the weight of a question no one can yet answer. Is this the beginning of something far more catastrophic? A pivotal revelation came through satellite-based InSAR technology, capable of detecting minuscule changes in the Earth's surface. The data revealed that in just 2 weeks, Mount Rainier's southern flank had lifted by more than 3 centimeters. While seemingly negligible to the human eye, such deformation in geological terms is deafening. This uplift was not due to thawing or erosion, but the upward push of magma, a silent, invisible force inflating the crust from within. Further anomalies were noted in the Carbon River Valley, a region choked with glacial ice and known to be a primary Lahar corridor. Should volcanic heat breach this frozen terrain, it could trigger a lethal slurry of rock, water and ice, surging down the valleys at terrifying speed, obliterating everything in its path. The crucial uncertainty remains whether warning systems would act in time to prevent mass casualties. Adding to the mounting concern, thermal imaging captured new hotspots in areas once considered geologically inert. Concurrent chemical readings detected rising emissions of volcanic gases, notably carbon dioxide and sulfur dioxide, both reliable indicators of ascending magma. Visible steam began to curl upward from the summit's fractured rim, subtle but unmistakable signs of internal activity. Below the surface, seismic networks registered long-period earthquakes, deep, resonant tremors that typically signify the movement of magma and superheated fluids. Unlike the sharp jolts of tectonic quakes, these were low, rolling vibrations, evidence of the volcano's internal machinery beginning to stir. Most disturbing of all, the mountain was not simply rising, it was expanding outward in a radial swell. AI-enhanced geophysical models flagged this specific deformation pattern as eerily reminiscent of those that preceded past cataclysmic eruptions, such as those at Mount Pinatubo and Mount Redoubt. In this light, the signals paint a portrait not of isolated geological activity, but of a system under immense and growing pressure, one that may be edging toward a breaking point, as if the Earth itself were signalling its intent. A new and unsettling phenomenon emerged from beneath the surface bursts of subterranean acoustic energy. Travelling as ultrasonic shock waves reverberated upward like the muffled echoes of distant explosions. These weren't isolated anomalies, but pieces of a larger, accelerating puzzle, evidence of a geological system under immense pressure, inching toward rupture. Experts liken the process to an immense subterranean balloon expanding rapidly beneath one of North America's most dangerous volcanoes. Though each signal might be scientifically rationalized on its own, their convergence weaves a haunting narrative, one pointing not to theoretical hazard, but to an impending volcanic upheaval. The debate has shifted. The question is no longer if an eruption will occur, but when in the depths beneath the Pacific Northwest, an enigmatic pulse has captured the focus of the seismological community. This rhythmic, low-frequency vibration recurs with uncanny regularity every 11 hours, defying all known natural and artificial patterns. Dubbed the Echo, it emanates from multiple locations along the west coast, but efforts to locate its true origin have only deepened the mystery. Some seismic readings suggest a connection to deep magma movement beneath Mount Rainier. Others point toward a tectonic anomaly near the Gorda Ridge offshore. Still, advanced simulations propose that the sound may not originate from a single source at all. Instead, it may be reverberating through vast subterranean voids, amplifying like sound in a sealed chamber under pressure. Whether caused by fluid migration, a newly forming fault system, or something entirely unknown, its implications remain unresolved and potentially profound. Mount Baker released faint trails of steam. Subtle but unmistakable seismic signatures began to flicker beneath Glacier Peak and the Three Sisters in Oregon. To casual observers, these might appear as typical volcanic activity in a tectonically restless region. But to volcanologists, the pattern was eerily familiar, one that hinted at a potential chain reaction, a broader regional awakening. Instruments at Mount Hood and Crater Lake revealed tremor patterns eerily similar to those preceding past eruptions, suggesting the possibility of a cascading geological event across the Cascade Range, an eruptive phase not witnessed in millennia. The implications are staggering. If the unrest at Mount Rainier is merely the prologue, what follows may test the resilience of an entire coastline. One eruption could conceivably trigger another, setting off a domino effect across the volcanically volatile corridor. Such a sequence could bring not just physical destruction, but a sustained societal crisis. This is no longer a story about a single volcano. It may be the emergence of a long-dormant rhythm in the Earth itself, one slow to begin, unpredictable in its course and devastating in its potential reach. When envisioning a volcanic eruption, most imagine columns of ash billowing skyward or rivers of glowing lava creeping down charred slopes. Yet the danger posed by Mount Rainier defies that typical imagery. Cloaked in more than 24 glaciers, the threat it harbours is not one of fire but of ice and water transformed into destruction. Should an eruption occur, the rapid melting of even a portion of this vast frozen mantle could trigger a lahar, an unforgiving slurry of mud, rock and meltwater. Unlike lava, which moves with a certain grim predictability, lahars rush forward with violent force, surging through valleys at speeds nearing 60 miles per hour. These torrents do not curve gently around obstacles, they consume them. Forests vanish, roads are torn from the earth, and communities are swallowed in minutes. Towns such as Orting, Puyallup and Enumclaw lie squarely within these lahar pathways. In the worst-case scenario, entire populations might have fewer than 40 minutes to evacuate. The past is not without warning. About 600 years ago, the electron mudflow, the last major lahar from Rainier, swept across what is now the Puyallup Valley. At that time, there were no highways, neighbourhoods or airports. Today, those floodplains are densely built up, full of homes, businesses and people who may not know the ground beneath them remembers catastrophe. This is not an alarmist tale, it is a statistical reckoning. Scientists emphasize that the question is not if Rainier will erupt, but when. The variables are chilling. How many lives will be lost, how swiftly events will unfold, how wide the devastation will spread. Already subtle signals hint at change. Seismic instruments record tremors beneath Rainier's summit, while magma chamber activity is closely monitored by volcanologists. Emergency planners run simulations in quiet rooms, imagining scenarios where lahar warnings must be issued in the dead of night or during a storm that mimics eruption-induced flooding. And yet, readiness remains patchy and inadequate. Recent system tests in towns nearest the mountain revealed disturbing gaps. Sirens failed to sound or went unheard in the din of daily life. Evacuation signs were absent in key locations, and entire rural zones lacked designated safety areas. In some schools, children had never practiced evacuation drills. Parents were left in uncertainty, unsure whether their families could respond quickly enough. Compounding the danger, misinformation spreads faster than lava. Social media platforms teem with false alarms, conspiracy theories and fake alerts that distort public understanding and erode trust in official warnings. In a moment where every second counts, confusion can be lethal. Still, Rainier looms, silent and majestic, hiding its unease beneath a glittering crown of ice. Over the coming weeks, scientists anticipate that volcanic unrest could escalate. Seismologists are modelling swarm patterns, hoping to catch early signs of an impending shift. But nature may not wait for perfect clarity. The next sign might not come from a satellite or a press release. It may rise up from deep within the earth, sudden and unapologetic. Mount Rainier owes nothing to the schedules of humanity. When it awakens, it will not consult sirens, maps or internet feeds. It will simply act. The choices made now by communities, by governments, by individuals will determine how many survive when the mountain finally speaks. If this video opened your eyes or made you think differently about the risks we live with, don't let that awareness stop here. Like the video to help spread the message, share it with someone who needs to hear this, and subscribe to the channel for deeper dives into the science, stories and strategies that could save lives when nature strikes. Stay informed, stay ready, and stay connected, because the mountain is listening, and one day soon it may answer.